Hello and welcome to my e-poster on towards routine global volcano monitoring using Sentinel-1 data and the LiCSAlert algorithm. This is work that I developed as a PhD student on the LiCS grant, also as a COMET postdoc, and finally as an ESA Living Planet Fellow. On this work I've collaborated extensively with Andy Hooper and Susie Ebmeier, both of the University of Leeds. The rationale for this work is that the Sentinel-1 satellites generate huge amounts of ground deformation data, and this data has really strong evidential worth for assessing eruption potential. But with 1,500 active subaerial volcanoes with new interferograms being created every 6 or 12 days by LiCSAR, searching for these signals manually in the data is a really onerous task. So if we take an example of the Eastern Pacific, green shows where LiCSAR is automatically creating interferograms. The darker colour here suggests a longer time series. If we zoom in on that one interferogram, you can see that many volcanoes don't have any signals of interest associated with them. But Sierra Negra shows this really clear deformation pattern. And it's the search for these deformation patterns in this huge set of data that we've been interested in and have applied machine learning to help us do. To do this, we've developed the LiCSAlert algorithm, which is divided into 4 parts. In the first, we simply divide our time series up into a baseline stage of perhaps 1 or 2 years, when we think that there's nothing, we didn't have any periods of unrest at the volcano. In the second stage, we can then use ICASAR, which is a Python package that I wrote for applying independent component analysis to INSAR data, and we can use that to find the latent signals that combine into each interferogram. So here IC1 is probably a deformation pattern located on the caldera. But just delving into that in a bit more interest, ICASAR is probably the one thing that lots of other people could apply to their own work. So in a little more detail, you can see that IC1 is a deformation pattern isolated, and IC2, when the algorithm compares it to the DEM, we can see a really strong correlation, and that's indicative that this is isolating a topographically correlated atmospheric phase signal. ICs 3, 4, 5 and 6 probably capture features of the turbulent atmosphere. Once we've done that, we can then perform a very simple inversion to fit each of these interferograms using the components we've learned, and we can then sum those through time. So for instance, if this keeps on being used in the same manner, we see the same gradient. We can fit a line of best fit through that to find our gradient. We can then set our algorithm going, and as we ingest new interferograms in real time, we can perform the same simple inversion and record how strongly each component is used to fit each of the new interferograms. But later on in the time series, we see a change in rate in the inflation at Sierra Negra, and because of that, we start to use IC1 more strongly. And when we sum how strongly we're using it through time, we then see a new gradient. We can't fit that with the line of best fit we learned in our baseline stage, and the volcano is flagged as having entered a period of unrest. So Sierra Negra is a really clear case, but we've also written a new version of the algorithm now over the last few months that works much more powerfully in cases where you'd have a much smaller signal that wouldn't be visible in a 6 or 12 day interferogram. We've applied this to Campi Flegrei at a time series of data there, and you can see that IC0 we pull out as the most important IC as a deformation pattern located within the caldera. And when we compare the DEM to IC correlations, we see not much in the first 2 cases. But with IC2, we see a really clear linear trend. So that is indicative that IC2 is probably capturing a topographically correlated atmospheric phase signal. We can also look at how the temporal baseline of an interferogram, i.e. say a 600-day base interferogram, might use IC0 very, very strongly, and that suggests that it's deformation, whereas the atmospheric signals, you'd expect it to be used no more strongly in a 12-day interferogram or a 120-day interferogram. When we apply the LiCSAlert algorithm to the full time series of data from 2014 through to 2021, we can see we don't flag the volcano, we don't have any false positives, we're not flagging anything. But what's really interesting, I suppose, to see is that when we look at IC2, we see a clear sinusoid through how strongly it's used. And remember that IC2 is the one we suggest as a topographically correlated atmospheric phase signal. And the seasonal nature of this, i.e. each of these cycles takes 1 year, suggests that we are capturing an atmospheric signal really clearly, and we are able to isolate it. So just to conclude, the LiCSAlert algorithm is in development and it's working on about 10 volcanoes at the moment, but it should be coming to more. And if you want to use any of the software, such as ICASAR, for looking at your own data and trying to isolate signals of deformation from atmospheric ones, then it's all on GitHub, and I'm more than happy to answer any queries you get in your use of it. So thanks very much.